All right, today we've got a story for you that, believe it or not, starts deep inside the Earth's crust, then jumps to a 19th century chemistry lab, and lands right inside a 21st century algorithm. Yeah, we're talking about aluminum. It's all about how we first unlocked this incredibly common metal, and now how we're perfecting that whole process with AI. So let's just dive right in. So, let's kick things off with a little puzzle, right? It's about a metal that is, and I mean this literally, everywhere. You see it in your soda cans, you see it in airplanes, it's all around us. Okay, here's a fact that honestly surprises a lot of people when they first hear it. You think about all that iron and copper, but forget them. Aluminum is actually the most common metal on our entire planet. It makes up something like 8% of the Earth's crust. Just think about that for a second. And that, well, that's the big paradox, isn't it? If this stuff is so abundant, then why in the world was Napoleon III serving his most important, his most honored guests with aluminum cutlery, while, the less important folks had to make do with plain old gold? The answer, as it so often is, comes down to chemistry. See, you can't just go digging and find a nice, shiny nugget of pure aluminum. Nope. It's chemically locked up, really tightly bound, inside this rock called bauxite. For decades, the smartest people on the planet just couldn't figure out a cheap way to get it out. It was like it was trapped in a chemical fortress. But then, a breakthrough. A huge one. So now, let's take a look at the brilliant 19th century chemical key that finally unlocked that fortress and made aluminum available to all of us. Okay, so the year is 1887. An Austrian chemist, a guy named Carl Bayer, he finally cracks the code. He comes up with this process that can efficiently pull pure aluminum oxide, which we call alumina, right out of the bauxite. And this method, the Bayer process, was so good, so effective, that it's still the main way we get our aluminum today. Incredible, right? So how does this thing actually work? Well, you can kind of think of it like a super clever four-step chemical recipe. Okay, so first up, step one, digestion. You take the bauxite, you grind it all up, and then you dissolve it in this hot caustic soda solution under some serious pressure. I'm talking like a giant industrial strength pressure cooker. Then, step two is clarification. You got to filter out all the gunk, right? All the impurities, which create this waste product called red mud. Next, step three, precipitation. You cool the whole solution down, and that causes these pure aluminum hydroxide crystals to form and just drop out. And finally, the last step, calcination. Those crystals get baked at over 1,000 degrees Celsius. This drives off all the water, and what you're left with is a fine white powder, pure alumina. And that's the magic. So yeah, the process is brilliant, no doubt about it. But when you apply it to the massive, massive scale of modern industry, a whole new challenge pops up. And this one is a race against time and inefficiency. And this quote from a research paper, man, it just nails the modern bottleneck. See, to keep this huge chemical process running smoothly, you have to constantly be testing samples. But the old school way of doing that analysis, it's slow, it's tedious, and getting the results you desperately need can take up to a full 24 hours. And you might be thinking, okay, a 24-hour delay, what's the big deal? Well, it all comes down to one word: scale. Just to give you an idea, back in 2018, the world produced 130 million tons of this stuff. When you're operating at that kind of level, you absolutely cannot afford to wait a whole day to find out if your process is running just right. And here's the really crucial part. That time lag, it translates directly into waste. We're talking huge amounts of waste. Every single hour that the process is even slightly off spec, you're just burning through energy, you're wasting expensive caustic soda, and you're getting less alumina from your bauxite. The costs, they just skyrocket incredibly fast. Okay, and this is where modern technology finally enters the story. So let's check out how artificial intelligence is being used to just smash through that efficiency wall and bring this 130-year-old process screaming into the 21st century. So instead of waiting around for those slow lab tests, people are now using machine learning. Basically, you feed these AI models a constant stream of real-time data right from the plant. We're talking about everything: chemical concentrations, tank temperatures, how long the stuff is sitting in the system. And the AI's whole job is to look at all that data and predict how to maximize the efficiency of that super important precipitation step. It's all about squeezing every last possible crystal of alumina out of the solution. And the results, well, they speak for themselves. One study showed that just by using AI to optimize the operating conditions, the average precipitation efficiency jumped from 42% all the way up to 47%. Now, a 5% leap might not sound like much, but in an industry this huge, that is a massive gain. And the best part? It was all achieved without any new hardware, just by being smarter with the data they already had. But hey, the optimization doesn't stop there. It's not just about producing the alumina powder. AI is also completely revolutionizing the very next step, smelting that powder into pure aluminum metal. And guess what? It's making that process faster and way more accurate, too. To do this, they use this really fascinating type of AI called a genetic algorithm. And it works pretty much just like the name suggests. It mimics natural selection, evolution. It starts by creating a whole population of random potential solutions. Then it tests them all to see which ones are the fittest or the best. Then it takes the best ones, combines them to create a new, even better generation of solutions, and it just repeats that cycle over and over and over until it finds the absolute best possible answer. Now, I know this flowchart looks a little complicated, but what you're really seeing is the evolutionary process in action. The algorithm pulls in raw data from the left, and then poof, it generates a whole population of possible answers. Then it runs them all through these competing loops. It's like a survival of the fittest, but for data, until it finally spits out the single best chemical composition. It is, quite literally, evolution happening on a microchip. So let's just put this side by side for a second. The old way? Slow. We're talking up to 24 hours, and it's all tedious manual labor. The new AI-powered way? It's automated, and it's way, way faster. But the really stunning part, the thing that just blows me away, is the accuracy. One study found the AI method was almost twice as accurate as the standard manual techniques. That's a game changer. Okay, so we've seen how AI makes this whole process faster and more accurate. That's great. But all of this, it's actually building towards something much bigger, a much more important goal. And this quote from an industry review really lays out that grand vision perfectly. The ultimate goal here isn't just about making aluminum cheaper, it's about making it perfectly. Imagine, zero emissions, no environmental impact, and absolutely no waste of energy or materials. We're talking about a truly circular and sustainable process. And really, that's the key takeaway from all of this. It's not just about saving money. Every single percentage point of efficiency that AI can squeeze out of these old processes means less energy getting burned, fewer raw materials getting used up, and less waste being produced for every single ton of aluminum. It creates this direct, powerful link between optimizing a process and making it sustainable. So we've gone on this incredible journey, right? From a metal that was locked away in stone to a process that's now being perfected by code. And it leaves us with this really fascinating question to think about. If AI can so completely reinvent a 130-year-old industrial cornerstone like aluminum production, what's next? What other foundational processes out there are just waiting to be made smarter, cleaner, and a whole lot better?